And we are back on the actual lecture now. So before the break, we talked about similarity laws, how to scale up, scale down, scale models, how to modify viscosities, how to modify sizes of models, and then we looked at different test facilities, for instance, wind tunnels, water tanks, and a few special systems. Now, I would like to spend the second hour on actual measurement methods. And let me switch to the slides again. This and here we go. So velocity and pressure measurement. So let's say we have our model installed in the actual wind tunnel water tank. Now we actually want to measure velocities, say in the wake of the object we want to study. So the most obvious things we can do are point-wise measurements, and we actually already looked at maybe the oldest and maybe the most famous and probably still one of the most widely used tools, and that is the pitot tube. Pitot tube in its simplest design is essentially just a simple tube, a hole, which is tapping the local pressure, and it can be measured with a manometer in the simplest way, or let's say with more complex pressure transducers. Now there's many sub-designs or less versions of a pitot tube, and there's also different names floating around. You will find things called the parental tube, or sometimes called the pitot-static tube. What this means is just different arrangements of the holes. And one thing we actually looked at in the lecture, I think was the third or fourth lecture, where we looked at conservation laws, where we introduced the Bernoulli law, was actually this system here, which is actually a parental tube or a pitot-static tube with a hole pointed to water flow, measuring the stagnation pressure, so the pressure of the fluid plus the contribution of, let's say, the kinetic energy at the stagnation point, and a tap on the side to measure only the pressure, and the difference between these two pressures corresponds to rho v squared divided by 2. What you will see very often in wind tunnel facilities is that people are using these 5-hole probes. So these are probes with multiple holes, and what these holes or what these probes can do, they can actually be calibrated also to measure velocities and pressures which are not directly in line with the main axis of the probe, so it can also measure different velocity components. One of the issues of all these, let's say, manometry-based pressure measurement systems or velocity measurement systems is their time constant. They're not very fast. And the reason for that is there's usually long pipes attached to it. So you need to displace a bit of fluid, actually as much fluid as you displace here in the water columns. You need to displace that fluid through these pipes. So if pressure is changing in time, you will obtain a pulsatile flow going forth and back in these tubes. So we have a pulsatile flow, and we know that pulsatile flow at high frequency goes into high Womersley numbers, and then we get very sharp shear layers, so it tends to block high frequency flows. So pressure changes at very high frequencies cannot really be measured with these devices. For that, the gold standard is the hot wire anemometry. The principle is the following: you have the probe on a little thing here, and maybe let's go to the schematic picture here. At the tip, you have a little wire that is heated up by a constant current. So you have a constant current which is heating up the wire, And if it's in still air, the wire will reach a certain temperature, and depending on the temperature, the resistance will change. So the voltage you can measure across this wire that you need to maintain this current has something to do with the temperature of the wire. Now, if this wire is subject to an airflow, it will cool off more quickly, right? So for a given current going through this wire, the temperature will be at the lower level. And that will again modify the resistance, so the voltage across the wire will change. So that's a way to actually measure velocities. So you measure how much the flow is cooling off the wire, and by measuring how much it's cooling off the wire, you can deduce the velocity that is present at this particular point. These devices turn out to be very accurate and actually very, very fast devices. At the same time, they're small, but they're intrusive. So you go into the flow with these devices, you're probing them, and they can be expensive to work with. Third method, and it's still a point-wise method, is a laser-based method. We're now coming into the field of optical measurement technologies. It's called laser Doppler velocimetry, or LDV. You very often just hear the term, the acronym LDV. So the basic concept is the Doppler effect. You probably know the Doppler effect like from acoustics, that if an object is coming toward you, the sound that it makes comes in at a higher frequency, and if the object goes away from you, the sound that it's emitting arrives to you at the lower frequency because of the speed of the object. The same goes for the scattered light. So if you look at a picture, the top picture, you have a laser beam at a given wavelength, laser light given wavelength, like coherent monochromatic laser beam, and this light is scattered off a particle. Then the scattered light will not have the same frequency as the laser beam itself. There will be a slight velocity shift because the particle is moving relative to the laser beam. And this little frequency shift can actually be measured. And the simple relation is that the wavelength times the frequency shift has something to do with the velocity. So this is sort of the basic Doppler principle that's being used. In practice, what you will see in most labs is an LDV system with two laser beams. They work slightly different. So you have two laser beams from the same light source, and they're crossing at a certain point. So you have a well-defined point in space where you're measuring. Now, because these two laser beams are crossing at a certain shallow angle, you will develop an interference pattern at the point of crossing. So there will be places where the two waves interfere in a constructive way, and there are places where they will interfere in a destructive way. So you'll obtain a fringe, so-called fringe pattern here, which then again illuminates the particle. And the particle flowing through this point will again emit light, and it will emit light which depends on the speed it has as it goes through this interference pattern. This is essentially the formula you get down here. The frequency of the light arriving here at the photodiode or at the camera corresponds to the velocity of the particle, actually the velocity in that plane here perpendicular to the plane of symmetry, times 2 sine phi, phi being the angle between the two between the two laser beams divided by the wavelength lambda. It's quite a good method. It's non-intrusive, right? You're not modifying the flow itself. You really just need optical access. And yeah, it works quite well. At the same time, it's only a point-wise measurement. You only measure at one point. If you want to understand the whole flow field, you need to scan through, or what people say, you need a global method. So question is, what types of global methods do we have? And maybe this little drawing on the right here already suggests what we can do. It already uses here one particle to scatter the light. And you can think of a system where you have a lot of particles in a flow field. And if you're able to know what these particles are doing, you can, with one view at all particles, already get an impression of what the velocities look like. That's why these global velocimetry methods are, maybe not all, but almost all of them, or many of them, are based on tracer particles. I have a little movie here just showing what such a picture could look like. I think this is probably the inflow through a little valve into a piston. You see the piston moving now to the left, and then moving out again. You can start again. The valve opening, inflow, you have a vortex down here, and then the piston is coming back up the cylinder, pushing it out again. And I think at least visually, we get a pretty good impression of what's going on. At least our brain does, I think, already quite a good job in modeling what is going on. We immediately understand that there's a vortex down here. We understand what the flow velocities are, what the flow directions are. And there are methods which are trying to quantify that, which are trying to make a, let's say, quantitative method out of that, not just a qualitative method. And these methods, they obviously all need a nice illumination of these particles. And that is not as straightforward as we might think in the first place, because if you have a volumetric flow, and by definition fluid flows are in a volume, they're in a pipe or in a more or less confined structure. If you have particles seeded throughout this fluid, and you just look through it, you will see the projection of all particles along your line of sight, and you have no depth information. That's the reason why most of these methods actually use a configuration that is shown here. Usually you only illuminate one light sheet. So you typically have a light source, you have a laser as a light source. There are also other options, but laser is the common light source that's being used. And you have certain optics, which is creating a thin light sheet, which is typically perpendicular to the main flow direction and perpendicular to your camera. Okay, so you have three axes: the flow axis, the light sheet coming in, and then the third direction, you have your view. In such a nice configuration that we see here, this looks quite straightforward. As soon as you have a bit of a, let's say, complex geometry, this can become already quite difficult in terms of arrangement. Where do you bring in the light? Where do you bring in the camera? Where do you have an unobstructed view for the camera? Where do you have unobstructed access for the light sheet? And of course, if you have this, you're free to move through or scan through the whole fluid volume with your light sheet optics. So as long as the flow is steady, many flows are steady, you can just scan through and scan the flow field in different planes. As soon as the flow is unsteady, or for instance, the turbulent flow, well, you will have a problem. You have to deal with that. Or what do you do in a pulsatile flow? Maybe you can do some phase averaging. So these are all issues that you have to deal with if you're setting up such an experiment. But let's stick with this simple configuration for now. Let's see what we can do with these pictures. The first method I would like to talk about is maybe the one that is intuitively the most clear. It's called particle tracking velocimetry, or very often it's just called by the acronym PTV. So what do? You seed your fluid with tracer particles. Keep in mind these particles should be passive in the sense that they should be small enough such that they do not affect the flow itself. So if the particles are on a similar length scale as your flow volume, then probably you will modify the flow. So in a typical tube, let's say for instance, where we study the flow in the aorta in our lab, we use particles on the order of 20 to 30 micrometers. So several orders of magnitude smaller than the length scales of the flow. Second step, we illuminate the particles. We just looked at this, how we're illuminating them with a light sheet. And then we capture the scattered light of these particles in multiple frames at a given time delay. So let's say we have a camera which just takes one frame after the other. We set the camera speed, how many frames per second, and we know that with every frame, the particles will have moved a little bit. And you see this down here in this in these two examples. So on the left, we actually have two video frames, two subsequent video frames just put on top of each other. So for each particle, you see actually two positions, position in frame one and position in frame two, and they're just added up to each other. And again, I think visually, or your brain already does quite a good job in connecting two neighboring particles and saying, okay, this is probably the same particle, and you can draw mentally a little vector between the two. And this goes even more easily if you add up 5 frames, or it can be even more. So now you already very clearly see the direction of the flow and also the length of this trace, or it's actually a streak line. The length of this streak line tells you something about the velocities. So the shorter the streak is, the smaller velocity. The longer these streaks are, like down here, the higher the velocity. So as long as you're able to identify a particle path from multiple frames, you can measure the displacement of the particles, and you can divide it to the time delay, because that's known, that's your camera frame speed, and you obtain the velocity. So the main difficulty of particle tracing velocimetry is the ability to identify particles that belong together. In the example that I'm showing here, I think this is relatively easy, but you can imagine as soon as you have more particles in the volume, it becomes very quickly very complicated to associate two particles to each other. Moreover, think of it, you have a 2D light sheet illuminating the particles. What happens if you have a 3-dimensional flow and one particle is in a light sheet and the next instance it has passed through the light sheet to the other side? It will no longer be present. So you need relatively sophisticated algorithms to detect pairs, or let's say families of the same particle. So this method, as simple as it is in the first place to understand it, it can very quickly become quite complex to work. I'll later on compare again these methods to each other. A second method, closely related but at the end different, is the so-called particle image velocimetry, or PIV. It's a method that has been developed, I think, sometime in the 80s, and is maybe by now one of the gold standard methods for global velocimetry in experimental fluid mechanics. The basic setting is exactly the same as what we do for particle tracing velocimetry. We also have a fluid seated with particles, we have a light sheet, and we capture multiple frames of the scattered light. But the difference is in PIV, at least in its standard form, we only need two frames at a given time delay. And instead of comparing these two frames and identifying pairs of particles of the same particle and measuring the distance between the two, we're not measuring or identifying single particles, we're matching patterns of particle images. So if you look at this diagram down here, you have one video frame here, the second video frame there. If you cut up this video frame in, let's say, larger windows, you'll have constellations of particles which look like that. At the same location, the same window, but the previous time, the other frame, the constellation will look slightly different. So if these windows are not too large, the velocities will be roughly the same in this whole window, and the constellation will have moved as a pattern. It's like a star sign you see on the sky at night, will have moved from one place to the other. So it's much more a pattern matching that you're doing than having to identify single particles. I'll talk in a second about how to do this matching. But in some sense, this is a statistically much more robust method because there's no need to say these 2 points on my 2 frames are the same particles. I just say I have a pattern and I look for the same pattern in the other frame. And I look how much this pattern has shifted, and the pattern displacement divided by the time delay gives you then the velocity vector. Now, how to do this pattern matching? There are actually multiple methods of doing this. I just would like to make one straightforward example. So we have the 2 frames on the left, frame 1 on the right, frame 2 at the time delta t later. First thing we do is we select a little window of size n times n. Whatever n times n should be, I mean, there's ways of choosing optimal n's. But for now, we just say we choose one window and we select a search window in the second frame, which we make somewhat larger. So the idea is that we take whatever pattern, which is now more like a pixel image. It's not the concept of individual particles. It's more like a pixel pattern of different intensities. And we go and check in the second frame whether we find the same intensity distribution of the pixels in the second frame. So we take the sub window, so we take this window here, and we shift it to the right by delta x, and we shift it up and down by delta y. And we compute the squared error between the 2 images. So I2 is the intensity pattern in function of x and y. X and y are the pixels in x and y. And I1 is frame 1 in x and y. And here we shift the window in xi, the window by delta x and by delta y, and we take the difference to the intensity pattern in frame 2. And we square the difference and we sum it up over the whole window, and that gives us an error. And obviously, with every shift position that we do in this 2n by 2n window, we will get one error value. So this is like the example. Gray is our little sub window, and large in white is the larger probing window in frame 2. Here they're at the same position. Here it's shifted up by x minus 2, y plus 2. Here it's shifted to the top right, shifted to the bottom, and shifted a bit to the lower left. And for each shift, we get a certain error value. And now we go and look, whatever shift has produced the lowest error value, and this is the most likely pattern displacement. So we're looking for the least squared error. We're looking for the shift with which the shifted window matches the frame 2 the most closely. So depending on the size of the search window, this error matrix, where we have the pixel shift in X, the pixel shift in Y, and the error plotted here on the Z-axis, might look like that. And in this example, we have a clear minimum here. So we can say, well, most likely, this is the correct pixel shift. Now, one of the cool things, and now we come into the point of accuracy, is that in PIV, we can actually do a sub-pixel interpolation. We have only shifted the image pixel by pixel, so that depends on our pixel resolution. But of course, particles or fluid mechanics, they don't know anything about the pixels, so they will move in whatever distances they want to move, whatever velocities they have. So most likely, the minimum pixel shift or the minimum error for this pixel shift is not the real minimum. So we can try to, this is now like just one cut, just one line out of this 3D plot. We can cut out one line, and this minimum here is probably not the best minimum we can find. We can actually use the local 3 points closest to this minimum and interpolate like a parabola or a Gaussian function through it. I just drew this here with a red curve. We just use these 3 points here and interpolate the parabola through that, obtaining a more accurate minimum than this point here. So this is how in PIV you can actually get a sub-pixel accuracy, if you like. So you can, you're not limited by your pixel size. Furthermore, there's a few computational enhancements that you can do. It turns out that the least squared error method that I just showed you is computationally not the most expensive, is computationally not the most effective one, because you compute quite a lot to get these maps. It turns out that a cross correlation of images, which is conceptually very similar, is much faster. Moreover, you can rewrite your cross correlation of images in terms of a Fourier transform, and then you can use the fast Fourier transform to compute these correlation maps and to identify the best match between the shifted window and the search window in frame 2. So that way it becomes computationally a lot more attractive, because you can imagine if you have a lot of these frames, if maybe an unsteady flow, you can compute a lot of data, and it's of interest to have an efficient method to compute your velocities, your pattern displacements. So we have now seen two quite attractive global velocimetry methods, PTV and PIV, and it's good if we just compare the two and just understand what their advantages and disadvantages, because both have pros and cons. In PTV, we're tracking single particles. In PIV, we're matching particle patterns. Right? This is the main difference conceptually of the two methods. One of the limitations, and this is one of the main limitations of PTV, you typically have a lower resolution. Why is that? You typically have a lower resolution because PTV requires that you can identify the same particle in two frames. If you have only few particles in a volume, that's easy to do. But if you have lots of particles, if you have a very dense particle cloud, and just go back to these pictures, you see here you have a very dense particle cloud, and it's quite difficult to identify which particle on this frame belongs to which particle on the other frame. And this is why PTV has this resolution limitation. You can only use few particles, so you can identify them. Having fewer particles means fewer points of information. This problem is not there in PIV. You don't have this limitation. Second issue is the problem of losing particles. I already explained that. You will have particles that will pass through the light sheet and are lost in the second frame. In PTV, you just lost the information. In PIV, of course, you have the same effect. Particles can also leave the plane, but because you're not tracking single particles, but more like constellations or patterns of particles, the method tends to be more robust to lost particles. Another difference, and this is not necessarily a drawback or so, it's just a conceptual difference. PTV always delivers Lagrangian information. We obtain actual motion patterns of particles moving through the fluid. That can be very beneficial in certain applications, depending on your research question. PIV is yielding Eulerian information. We look at certain search windows and just try to understand what velocity we have inside the search window. Okay, so conceptually, Lagrangian versus Eulerian. And the last two differences are with respect to the equipment that you need to run these experiments. In PTV, you typically need a high-speed camera to have enough frames per time. Of course, this depends on the flow velocities that you want to study, but the faster the flow goes, basically you need a faster camera. And together with the camera, of course, you need for each frame that you take, you need light. So either you have a continuous laser, but continuous laser very quickly will require a lot of energy. So you need quite a lot of light to get the illumination for the particles. So in many cases, instead of having a continuous laser, people are using a pulsed laser because you can actually bring out more energy in the single pulses. And these are called high-speed pulse lasers, and their price goes up quite exponentially. So they can become really, really expensive, these devices. Whereas in PIV, devices are also expensive, but the problem is a little bit less dramatic because you get by with so-called PIV cameras, which just are fast and just taking 2 frames immediately, one after each other. So you don't need like a continuous high-speed camera, just a double frame camera and a double pulse laser, which essentially are 2 lasers coupled to each other. So the equipment has a tendency to be less expensive. This might not always be true, but that's just a general comment. Okay, so you see both methods have their pros and cons, and it always, as always in every experiment, it depends on your research question, depends on your application, depends on the material and the facilities you have around to decide which method is the best one for you. Let me just look at a few extensions. What I showed you are 2 standard global velocimetry methods. Both of them are limited to 2D flows. There are a few extensions, and I would like to highlight at least 3 of them. The first extension actually has nothing to do with 2D versus 3D. It's actually a problem that is quite common, that if you have a model that is, let's say, geometrically quite complex, so you'll have interfaces, and your laser light might not just scatter at the particles, that's the scattering light you actually want to see, it might also scatter like at the surface of your model, like your little aircraft model that you designed, and you get reflections from your aircraft model, which is messing up your image, your particle. So one way to deal with that is to use fluorescent particles. So instead of the scattered light, we are measuring the light emitted by fluorescent particles. What you see on the right is a little diagram which shows what this fluorescent dye is actually doing. So these particles are usually coated with a dye that is fluorescent. It takes light with this curve. So these are wavelengths of light, and this is the intensity. So this is like light, which is peaking at 550 something nanometers. This is typical light emitted by a green light laser. So either this green light can be scattered by the particles, or if you illuminate a fluorescent dye or a fluorescent particle with that, it will take that green light and emit light at a slightly higher wavelength, which turns out to be more like an orange light, okay? Or it's more toward the red, toward higher wavelengths. So what you can do is you can actually put a filter in front of your camera, which filters out all the green light from the laser and only lets through the fluorescent light, okay? This is one method which works really well, how to eliminate problems, artifacts from light scattering from your measurement device. So that's one thing you can do. Second thing and third is actually addressing the problem of 2D. Classical PIV, but also PTV, can only measure velocities in the 2D sheet and only the 2 components in the sheet. So this is why they're very often called 2D, 2-dimension, 2C method, 2 component. One extension of this classical PIV method, which you see on top of this diagram, the 2D, 2C method, is to use 2 cameras, which are arranged at a certain angle to the light sheet with a certain thickness. And because you get different projections of the velocity vector in these cameras, you can actually compute the 3rd velocity component. You're still confined to the 2D plane, but in this 2D plane, you can at least compute also the 3rd velocity vector. That's why they're called 2D 3C methods. So this is stereoscopic PTV, stereoscopic PIV. The third generalization of this concept is a method which captures actually volumetric information. So instead of illuminating just a sheet of the interrogation volume, we illuminate the whole flow volume. That's actually what we're doing in our lab to measure the flow past the heart valve, because this is such a 3-dimensional flow. It's important that we capture the whole complexity of the 3D flow field and not just one slice through it. Also, scanning through it would not be possible because it's a highly unsteady flow. These methods are called tomographic PIV or 3D PTV methods. There's one step in between, or one novel step, is that you need to take, in that case, the 4 images, which are 4 2D projections from different angles, and you need to reconstruct a 3D particle cloud. And there are mathematical methods to regenerate the most likely particle cloud in 3D. So you have a voxel space then with intensity, not a pixel space, a voxel space coming out of 4 different pictures taken from 4 different angles. So these are a few extensions to these global measurement methods. Let me close this lecture with just a few glimpses at other measurement methods. There are many, many other methods, and it's difficult in one lecture to look at all of them, but I think I showed you some important ones, and I finish with 2 more. One is called pressure-sensitive paint, so we're back to pressure measurement now. This is actually a paint that you can use to coat a model, and this paint is sensitive. Well, if you look in detail, it's actually not sensitive to the pressure itself. It's sensitive to oxygen concentration, or the partial oxygen pressure. But of course, this is directly related to the fluid pressure. So what happens is actually that you have so-called luminescence molecules, which are modified by the concentration of oxygen on the surface. And if you illuminate these molecules or stimulate these molecules by a certain wavelength, usually this is UV light, they will emit light, they are fluorescent, and this fluorescence will be brighter for lower pressures and dimmer for higher pressures. And what I'm going to show you on the next picture is actually a model of a rocket. I think this is a rocket from NASA, and they have put one of these models in a wind tunnel at a certain angle, and you see on top here the scientists in the UV light and how this model is emitting light. And if you analyze the light, I don't think you can really see it with the bare eye, so you need to analyze what you have with the camera, but then you get these very nice measurements of surface pressure. And the cool thing about this color, about this paint, is it's highly dynamic, so it's very, very fast. It can respond very quickly, and so you can very nicely see, for instance, here in these locations where you have some repeated vortex shedding coming off probably these corners here. You obviously have turbulent wall shear stresses here, probably coming off these little flow separating vortices. Huh? So I think these are really nice experiments and show the power of this pressure sensitive paint, or PSP as it's known in the acronym. The last thing I want to show you is something I've actually seen already a few pictures last week when we talked about compressible flows. It's called Schlieren imaging or Schlieren photography, or well, there's many other names, but the main thing is the word Schlieren, which actually doesn't just sound German, it's a German word for a streak. So it actually is, it's an optical method, and it captures density variations. So if the density of a fluid is changing, the refractive index of the fluid is also changing, and the optical refractive index. So light is slightly distorted. And the way these Schlieren imaging systems are set up is that they will measure gradients, or the brightness corresponds to high gradients of refractive index. So wherever the refractive index changes a lot, we get a bright image. And this is why in this picture here, we see this bow shock, this detached shock of this supersonic projectile here very nicely as a bright curve. And this is where the refractive index is changing very rapidly, confined to this shock and all the other shocks. So this is a very popular method in transonic, supersonic flow research to visualize these phenomena, because obviously their density is varying. In incompressible flows, density is not varying or varying only, well, now by definition it's not varying, so there's not much to see. It is also used for non-supersonic flows, but also for slow flows, that flows with buoyancy. So for instance, this here, I think this is a candle, and you see the plume of hot air rising from the candle and creating all these structures, right? So it's heated up air where the temperature is changing, you have a density change, and you can visualize that. And here on the right, essentially the opposite. You have a little popsicle here, which is obviously cold. It's cooling off the air, and the cold air is dropping down and creating this, let's say, inverted plume going down. One application I think is quite timely to look at this now is actually a visualization of air coming out of her mouth. It's hot air, so there's a gradient in the density, and this one can be visualized with Schlieren imaging. Let's look at this. This is something which was recently put online by a group, I think, in Weimar. So they visualize the air coming out of your mouth. So let's look at what it does. It starts on the top left, normal breathing. And you can see, it's a bit difficult to see, but I hope you can see it. You can see here plumes of air coming out. By the way, this here is just the heat of the body coming out. And this guy is coughing now again, and you see how he's spreading out whatever comes out of the mouth far out. He holds his hand in front of the mouth. It helps a little bit, but still it goes far. Coughing into the sleeve, even better. Coughing into a dust mask. It goes about that far. And finally, we do have the surgical mask here, and it goes about that far. So not that much magic behind it. It's just modifying the flow. The flow doesn't reach that far. It's just creating an obstruction. So I think this is, in these times, an interesting video and somehow close the loop and finishes this lecture. I don't think we need to see that. We can just switch back. Yes. So this is the end of this lecture. I think we're more or less just in time. I will stop the recording now and we'll make a few announcements then for next